So welcome to the second lecture, dealing with metal complexes, or more generally, coordination chemistry. Like we said, one of the discoveries that Werner made was that cobalt had two different things going on when it formed compounds. One, if it was a metal cation, it needed a certain number of anions associated with it to make it a compound. On the other hand, those ions were not necessarily bonded together. Like we said, ions are attracted to each other, but they're not really bonded to each other. At the same time, the cobalt was actually interested in being bonded to things. But the bonded things didn't have to be other ions. They were what we call ligands. And so what's the cobalt getting out of this arrangement? How does this work? Why would it want to be picking up some number of other things to just hold on to? We've been talking about bonding till now, but we've been looking at it at the two extremes. That is, whether the electrons are being shared more or less equally, or if they're not being shared even at all. Where they're getting shared, we of course are getting covalent bonding. And while one of the atoms is often more electronegative, and so the sharing isn't necessarily equal, it nonetheless is still a significant amount of sharing between the two. And as a result, we get molecules where the atoms are in fact all strongly held together by the covalent bonding. At the other end of the scale, we have, of course, the ionic compounds. Some of the atoms gain electrons, some of the atoms lose electrons. And as far as sharing goes, they're basically not sharing each other. What's holding the ionic compounds together are the simple attraction between the ions. And so they're not actually in any way stuck together, they're simply attracted to each other. But nature doesn't deal in black and white. Nature always talks about grays. And so now we're going to talking about metal complexes, where the electrons are sort of being shared between the two. The ligands are donating a lone pair of electrons to form our coordinate covalent bond, but they're not letting go of them, and they're not forming the strong kind of covalent bonds we see in the molecules. So what are we see happening in our metal complexes, or generally coordination compounds? Well, we have a metal center, and around it surrounded its ligands. The ligands, of course, are acting as Lewis bases. That is, they're donating a lone pair of electrons to form a coordinate covalent bond. So what do we see happening? Well, if we start out with cobalt, cobalt all by itself has 27 electrons. If we form a cobalt plus 3 ion, it now has 24 electrons. And so it's clearly electron deficient and would like to have more negative charge around it. Which brings up the 6 ammonia molecules acting as ligands. Each of the ammonias has a lone pair, and it donates that lone pair to the metal center to form a coordinate covalent bond. And so basically the metal is getting 2 more electrons around it. There are 6 ligands, so altogether the ligands are contributing 12 electrons to the cobalt center. 24 and 12 is 36, and of course, who else has 36 electrons? That's right, krypton, a noble gas. And so what we're seeing the metal complex do is basically a variation of the octet rule. For the main group elements, which are only a couple of electrons away from a noble gas, they only have to gain or lose a couple of electrons, form a couple bonds, and they get to their octets. The transition metals, of course, aren't anywhere close to a noble gas count. And so they have to gain a lot more electrons if they're going to get to a noble gas. And that's what, in fact, the ligands provide. They donate electrons so that the metal centers can work their way up to the next noble gas. And this is known as effective atomic number. So one of the things we're going to have to do when we look at coordination compounds is reassemble them from the formulas we usually get given, which simply indicate an ionic compound and some number of other stuff just sort of hanging out with it. and assemble it into, in fact, the complex ions formula, where the metal and the ligands are indicated as one particular piece. So consider these three compounds. What would be the correct formula for this? Well, in the first one, cobalt, as we've said, likes to have 6 ligands around it. In the second one, platinum wants 6 ligands around it. And in the third one, the silver wants 2 of the ligands around it. And so what are the formulas going to come out to? Well, for the first one, like we said, the rules for writing formulas are you use the square brackets to indicate it's all one complex ion. You list the metal first. You then list the ligands in alphabetical order, so the ammonia comes in front of the chlorine. We need 6 ligands, so it's the 5 ammonias and 1 chlorine get to be in the inner sphere, that is inside the brackets, and the remaining 2 chlorides are simply outside. They're in the outer sphere, they're only associated with the ionic attraction. For the platinum, all 6 of the ligands end up inside, that is all the ammonias, and all the chlorides in this case would be on the outside as ions. In the last case, the silver is coordinated to 2 of the thiosulfates, and there are 2 of those complexes. In this case, the complex is in fact forming an anion. So it is the calcium which is the lone ion by itself out in front, and the metal complex is the anion part, and there are 2 of them. Which brings us to everybody's favorite nomenclature, naming coordination compounds. The point is, when molecules and ions act as ligands, they have their names modified to indicate that they are in fact acting as ligands rather than as molecules or ions. The usual way of indicating that an anion is now in the form of a ligand is to take the ending, either the IDE or the final E, if it's a complex ion, and simply replacing it with O. And so bromide becomes bromo, and carbonate becomes carbonato, etc. Some molecules, which are frequently used as ligands, have special names, the most obvious one, of course, being water. And ammonia. You'll notice that ammonia is named as imine. It's got 2 M's in it. That's because a common organic compound is amine, that is with 1 M. So you have to be careful about that. You got to make sure you use 2 M's for the ammonia. Carbon monoxide is known as carbonyl. Nitrogen monoxide is nitrosyl. Molecular oxygen is simply dioxygen, and molecular nitrogen is simply dinitrogen. The rules for naming metal complexes are fairly simple and straightforward. First off, of course, you always list cations first, anions last. And in this case, it's sort of the opposite of writing the formulas. In the formulas, you use the square brackets. You list the metal first and then the ligands in alphabetical order. When writing the names, you start with the ligands, again in alphabetical order, using their ligand names. Use prefixes to indicate how many of each ligand you have, and then you come to the metal center last. And that is all one word. Occasionally, the metal complex ends up being an anion, and in this case, the metal gets an ATE ending to indicate that it's part of an anion complex. And so to name our 3 compounds, the first one has ammonia, so it's amine. Make sure you get the 2 M's in there. There's 5 of them, so it's pentaamine. There's 1 chlorine, so monochloro. And the cobalt is a +3 ion, so it's pentamine monochloro cobalt 3 is the complex, and then we have chlorides. And as with any ionic compound, you don't list the number of counterions. For the platinum, it's hexamine, platinum. In this case, the platinum has to be a +4 to balance the 4 chlorines, and again, just chloride. And finally, just calcium, since the calcium is a cation by itself. Bis. We have to use the modified prefix because we already are going to have to use the prefix di for the thiosulfito ligands, so it's bis. And we have 2 of them. So bis, parentheses, dithiosulfito, that's the correct name for that ion. Argentin, yes, it's silver as an anion. So it's argentate +1. So let's try a couple more. How would we go about naming these 3 complexes? Take a minute, see if you can come up with the names. So in the first one, our cation is simply ammonium. C2O4 is oxalate, so is a ligand, it becomes oxalato. We have 3 of them, and so it could be trioxalato, but you don't usually like vowels next to vowels, and so we use the somewhat modified tris rather than tri. So tris oxalato, iron, but of course it's in the anion part, so it's ferrate. And since the ammonia is providing a +4, the oxalates are each -2 is -6, and so the iron has to be +2. In our second one, we again have amines and chlorides. In this case, it's tetraamine, dichloroplatinum. And since the chlorides are each -1, the sulfates are -2, the platinum must be +4, and sulfate. And finally, potassium, hexacyano, difluoro, molybdate, since of course the molybdenum is as an anion charge, the cyanides are each -1, the fluorides are each -1, and so we have to get a total charge of +8. The 3 potassiums are +3, so the molybdate must be +5. And that brings us to the end of our lecture today on naming complex ions. Have a nice day.